Hello, and welcome to today's webinar on the APL problem solving competition. Never mind. So the APL problem solving competition is just around the corner. It has been running since 2009, and this year is our 11th edition of the contest. So to start with, the key dates for this year. The competition will launch in early May. We're hoping for sometime in the first 2 weeks of May. To keep updated for when the competition launches, go to dialog.com/student-competition, or just Google Dialog competition and it should come up near the top. This page will be updated with a link to the competition website when it goes live. The submission deadline for this year is Friday the 26th of July, which should give you over 2 months to have a go and submit your entries. And the winners will be announced on Monday the 5th of August, with the grand prize winner being invited to talk at the Dyalog user meeting, which this year is in Elsinore, Denmark, from the 8th to the 12th of September 2019. So if you're looking to win the grand prize, keep those dates free. And make sure you are able to travel. We are live on dialog.tv, so if you're watching from there, there are moderated chat. There's a moderated chat below where you can comment throughout the webinar. There's also great prizes for the competition. I'll show you on the competition website. When it goes live, will look something like this. The content is subject to change, but here we have a description of all the things you need to know to compete, and here's a description of the prizes. So the competition comes in 2 parts. There's phase 1, which are these on the left, 10 simple problems which can usually be solved in 1 line of APL. And then there's also the phase 2 part, which is a section of much more involved problems. So this year we have 3 easy, 3 medium and 3 hard difficulty problem sets. And you, in order to be eligible for the phase 2 prizes as a student or for the non-student prize, you will need to complete at least 1 easy, 1 medium and 1 hard difficulty problem set. So there are prizes, $100 US cash to each of the top 10 phase 1 entries. There are 5 random prizes to people who submit completed phase 2 entries, and they'll just go to random participants. Then there are also the top 3 prizes for the best quality phase 2 entries. There's also a non-student prize. So the grand prize is $2,500 cash and an invitation to attend the user meeting this year, including expenses paid for, travel expenses up to $3,500 and $500 for other incidental expenses. The non-student prize will have complimentary registration and accommodation for the Dyalog user meeting, but they will need to make their own travel arrangements. Now, if coding if entering this competition sounds quite daunting, you don't even have to be a student or have to enter in order to win prizes, because we also have referral awards available. If you refer someone, tell someone about the competition, and when they submit their phase 2 entry, they tell us that you have referred them, you'll be eligible to win an equivalent cash prize to the prize that any winners that you refer also win. So that can also be multiple winners if you refer all of them. For example, if you introduced a second prize winner and 2 winners of the phase 2 prizes, the second place prize is $1,250 and the random phase 2 prizes are $200 each. You could win $1,650 if you referred all 3 of those competitors. So that's the competition this year and the prizes. Now I'm going to talk about some of the problems that we've used in previous years with the aim of explaining some of the things that we think about when we judge the entries. What are the type of things we look for in a good submission? So the first one I'd like to talk about is the sample problem. For most, if not all of the years when we've had a phase 1 and phase 2 to the competition, the sample problem has been this counting vowels problem. So write an APL function to count the number of vowels A, E, I, O or U in an array consisting of uppercase letters. And we usually give some example solutions to demonstrate the difference between something that isn't fully optimal, I guess we'd say, it says suboptimal here, to something that is much neater APL that would be judged much more highly. And this year, for the first time, we have automated validation of our phase 1 entries thanks to Try It Online. Now, Try It Online is a family of online interpreters for a whole slew of programming languages. I mean, I don't know all of the programming languages, but this seems like most of them. So if you want to try out different styles of programming, go to tio.run and you can try all of these different languages, including, if you scroll down a bit, several flavors of Dyalog APL and a couple of other recent independent APL implementations. So thanks to Try It Online for enabling this. So on the competition website, in the phase 1 sections, you can enter your solutions and you can test your submissions. There are 4 sort of replies you'll get depending on whether you get errors or you get incorrect responses. And in this case, this solution passes the basic tests, but it doesn't work for higher than rank 1 arrays. So in the how to participate section, we include some advice on the types of things that we use to judge the submissions. One of them is the use of array-oriented thinking, and that's sort of exemplified in this long-winded dfn here, which tests all of the vowels individually and then sums up their instances and then sums all of those sums up, and it's just very long-winded. Something like this is what we consider more array-oriented thinking. But also, we want to check generality. So does your function handle the edge cases, which we do test for in the automatic validation, or is it even more general than required? So for this example, to pass the edge cases, all we need to do is ravel our enlist matrix. So this part here tests if AE returns a Boolean array where 1 indicates where an A, E, I, O or U appear in the array to the right. But that array will have the same shape as the array to the right. In this case it would be 2 by 3. So in order to be more general, we can ravel the array into a vector, sum up the instances of the vowels occurring, and we should have a solution that passes all the basic and edge cases, and we get a nice little gold trophy. Even more general than this, I can see that we have some data inside the function which, if you think about it, we might not want to just count the vowels. We might want to count any set of characters. And a way to make this part more clear might be to set a dyadic dfn with a left argument of our vowels and use jot, which is this symbol here, to bind our left argument as alpha. And now it becomes more clear that this is the core functionality and this is potentially variable data. Something slightly even more potentially neat, poor phrasing, could be to have a ambivalent dfn with a default left argument. So now, if I submit this, the alpha is still A, E, I, O, U, but I have the option of choosing a different set of characters on the left. The next thing I'd like to talk about comes from last year's phase 2. It's an easy part of the problem set. And with phase 2, the easy parts are more or less maybe slightly harder, but of the same caliber of difficulty as the phase 1 problems. So the easy part of phase 2 are usually about as easy as the phase 1 problems. In this case, the task was, so in APL we have this sort of set of puzzles we call broken keyboard puzzles. So imagine that your keyboard's broken and you can't access one of the keys, which usually means you can't use one of the primitives. So how would you implement that same functionality without using the primitive, in this case, greatest common divisor? So we had a couple of entries which I think are worth contrasting. One of which is this solution, which is a tradfn, which is dyadic. If you look on the Wikipedia for greatest common divisor, under Euclid's algorithm, this solution is a straightforward copy implementation of the fact that greatest common divisor of two numbers is equal to the greatest common divisor of one of the numbers, and then the numbers modded, a mod b, a mod b. So in this case we have this recursion, well, b is not equal to 0, a and b get b, and b mod a. And this works okay, except we get an error when you try to use an array right argument. That's because we have this Boolean singleton expression in the control structure, so it doesn't apply to array arguments. We can sort of force it to apply to arrays by binding a left argument with jot and using each, but it's not particularly elegant. A better solution is this one, submitted by last year's winner, Alva Björk. It's a guarded dfn where we ask if we ask if all of alpha equals 0, then we return the result. And this is an implementation just below. It's the same Euclid's algorithm, but this is the repeated subtraction version, which you can see here. So the greatest common divisor of two numbers is the greatest common divisor of the difference of the numbers and the other number, if so a minus b, and b if a is greater than b, and vice versa. Well, what's quite nice about this one is we have this tacit train recursion. So we have the lower of alpha and omega, and on the other side the greater minus the lower. And in one line this covers all of three of those cases listed here, and that's just really quite neat. What's more is because of this and reduction, this function applies to arrays just straight out of the box. I think it's also kind of worth noting the difference in runtime. So there's this user command square bracket runtime that allows you to compare a set of arguments. Computational speed isn't a super high priority judging criterion, but oftentimes if you've used a more array oriented approach, you will get faster results. So in this case, the modular version, I'll put them both here. In this case, the modular version is faster for individual results, for individual arguments, single argument A and B, but it gets much slower as you apply large arrays to it. And most of the reason it's faster is that the modulo version gets to the result quicker than the repeated subtraction version. Now, as I said, runtime isn't really... Oh, one more thing worth mentioning actually. I believe runtime is basically a wrapper for the dfns cmpx function. And if you go to the dfns website, which is dfns.dialog.com, you can find some performance related functions which are already written here. They might be useful to you, so I thought I'd mention them. There's also a profile function to help test the individual parts of your functions. Also, interestingly, dfns already has a greatest common divisor page. I mean, it's a whole bunch of different greatest common divisor implementations, including this array-based one, which is very similar in terms of its recursion, checking if they're all zeros here in a slightly different, possibly faster way. And this recursion is basically identical to the one that Alva submitted here. So, as I said, speed might be worth looking at, but isn't a top priority generally. Something that is more important is if you have a really fudgy solution. And by fudgy, I mean it works, but you can tell that you've kind of just gone into the interpreter and typed things and tried things out until you got the solution you're looking for, and then you just said, well, I'm done. And that's what you submit. And it's usually quite straightforward to tell. So for an example of this, I looked at 2018, same year, but this was phase 1. Looking at whether 2 character arrays were anagrams, which are character arrays with the same number of the same characters, ignoring spaces. So I wrote this ugly hacked solution. The first bit doesn't look too bad. We removed the blanks because we're not interested in them. The fact that there's a diamond isn't great because phase 1 should usually be 1 line, and using a diamond is kind of cheating and makes it 2 lines. But the main faux pas, the real ugly bit, is this nonsense here, this confused misuse of dyadic iota, the index function. So dyadic iota, if I have 2 arrays, will tell me where in the left array appear the elements of the right array. So O does not appear in the left array, so it's given a value 1 greater than the shape of the left array. C appears in the 3rd position, so that's what we get here, and B appears in the 2nd position, so that's what we get here. I mean, this is really just a bit of nonsense. If you know that your 2 input arrays have the same number of the same characters, if you just apply the sorting idiom to each of them, you should find that they end up as the exact same array. And then you can use a match reduction on that, and you can then have a Boolean test, are these anagrams or not? The example given in the problem statement is Albert Einstein, if I can type, is an anagram of 10 elite brains. But with the extra space here, this doesn't work. But of course we said we're ignoring spaces, so I can just easily ignore spaces for both my arguments. And now it works. And this is a much neater, sensible solution that shows more of an understanding of APL. One last thing I'd like to mention with regards to phase 1 solutions comes from 2016's phase 1 problems. We have this problem 9, delimited text. So we want to separate a character array of delimited values with an optional delimiter as a left argument and turn it into a nested vector of those character vectors. So that works for comma separated values, or if you want to break up words that are space separated, etc. Now in APL we have three sort of ways of writing functions, really. Three main styles, I'd say, for APL in Dyalog. Those are tradfns, dfns and tacit functions. And if you provide a solution, if you provide solutions that are equivalent, we won't judge higher or lower based on which style you choose. That's really a matter of personal taste. So I'm just going to give the solution to this problem in all three styles, just to show you what I mean, and you know how they're exactly the same. So a dfn version would take, so let's do a space delimited dfn alpha not equal to omega for this text will give us a Boolean array of where a 1 means it's not a space. And then we can just use partitioning close on our text and we solve the problem. A tradfn version, we can write a tradfn using the del. Our result gets the delimiter. I'm going to call it delimit. You have to name a tradfn. Some people see that as a disadvantage, I suppose. Whereas tacit and dfns, you can have unnamed ones and just use them like that. And some text, which we'll call t. And our result is, well, it's the exact same thing. So where does the delimiter not match the text? Partitioning close the text. And this is not going to work. How have I done this? Never mind. There we go. Happy days. And once again, let's just try it out. This text does the same thing, but in a tradfn version. I'm sorry about how that looks. Mistyping. The tacit version I think is just really neat for this one because it's just 3 characters, space delimited, this text. So these are the exact same solution, just in the 3 different styles. And as I said, we won't mark differently depending on which style you choose to use. So, advice for phase 2. Now, because phase 2 are some more involved problems, they usually consist of maybe a handful of individual subtasks. So, of course, they're going to consist of probably multiple APL statements in some kind of, sequence or combination. And so, therefore, the advice for phase 1 problems definitely applies to phase 2, but with phase 2 submissions we take more of a holistic approach. We look at not only the quality of your individual lines, but the way you've used APL to express the solution. So a winner of phase 2 might not necessarily have the most computationally efficient in code line by line, or they might not have the most mathematically reasoned code completely. But they might have used APL in a really expressive way or interesting way as a tool of thought, and it could be really clear sometimes just from reading the code what the intention of each part of the solution is and what they're intending to do in the solution. Of course, we also recommend commenting well on your code because that really helps us to see your thought process, and also helps to sort of demonstrate your enthusiasm for it, really. So the example I'm pulling up now is the submission from 2011's grand prize winner Joel Huff. I believe he submitted solutions to all of the problems, so that never hurts. For example, if we have 2 phase 2 submissions that are of indistinguishably good quality, we might use the fact that one person solved a couple more problems as a sort of tiebreaker. But the other more important things from this example are, well, the first thing that stands out is the comments, really. So Joel's explained what each of the arguments and what the result is expected to be. This helps a lot with multi-line functions. He's explained what each part of the code does. So this first section, he's naming the function something sensible so that later on it's clear what the code does based on the names of the functions in there. I guess you don't have to do this, but it can help to make things more clear. And then here, this just normalizes the convolution matrix unless it sums to 0 or less, at which point it's worth explaining what the problem is. So in 2011's phase 2, we had an image processing task, and this consisted of applying a convolution matrix to an image. And convolution is something you do in image processing when you want to blur or sharpen or emboss or do edge detection. GIMP and Photoshop, all those image processing applications will have this functionality. So here we're doing it in APL. So a convolution matrix might be something like this 3x3 matrix. Doesn't have to be this shape, but that's commonly used. And then you multiply that matrix by 3x3 sort of sections of the whole image, and then sum that result to get the new value of each individual pixel. Hopefully that'll become more clear in a second as I explain Joel's code and he explains it as well. This is almost bordering on overkill in terms of commentary, but it was really nice to see Joel really thoroughly explain his thought process and why his solution came out the way it did, why it contains the things it does. So for instance, he has this first idea of doing dyadic rotations, which I'll show you in a second, which are all creating these n by m being the size of the convolution matrix sections. So that's these sections of the image that you're going to apply the convolution matrix to. And he says this is a neat way to do it, but it will quickly use up memory if you have a large convolution matrix and a large image. So to get around that, he made another version of his algorithm that doesn't copy the image, but he calls it array slicing, but to my mind, this is starting to sound like stencil code. Again, I'll explain this further in a second. So to get the best of both worlds, we have an error guard on a WUS full error. So I have typed up Joel's solution without the comments. This first part is naming. Second part is normalizing the convolution matrix. So in this case, we're going to use a sharp edge detection algorithm, or quite a high contrasty one. This error guard here is where it says, if we get an error message 1, which is workspace full, go and use this other code that will finish off the job. But this version is faster, so if the workspace doesn't fill up, use this. And to my mind, there might have been an improvement if he'd just found the size of the image, or realized that the size of the what's the size of the image multiplied by the number of times I'm going to copy it, for instance, instead of waiting for the workspace to fill up. That might have been something to improve it, but this is just really cool that he's gone to this effort. This problem set came with a helper function to let you show the image, so I'm going to do that now just to let you see. This is the image that we're going to apply the convolution to. There was also a second part of the problem, which was apply your convolution to each of the red, green and blue channels of a color image, and that's required if I'm going to show the convolution of logos. So the problem statement for the red, green, blue part had contestants creating a separate function that would apply their function to red, green and blue, but here I've just turned it into an operator which applies our left operand argument to each of the channels. But this is based on Joel's code. I've just appropriated it for my own purposes. So I'm going to step through this and sort of talk through what's going on. So we're copying, well, we're renaming our arguments and normalize the convolution matrix. There is no workspace full, so we'll skip over this part. And then here's the cool bit. CY and CX are these kind of offsets based on the shape of the convolution matrix, which is 3 by 3, which is why they're each length 3 vectors. And those are what's going to create these rotated chunks. So if I take CX, rotate each, you can see I'm just copying parts of the bottom here of the enclose of, I'm going to demonstrate with the 3 by 3 matrix of letters. We have the original matrix in the middle, and on the left and right we have the -1 rotate and the +1 rotate. The next part takes CY, does an outer product rotate in the other dimension, in the perpendicular dimension, and now we have something which basically resembles a stencil, except, well, I'll show you how it's basically identical to stencil. So if we enclose using the stencil operator, which is new since recent versions of Dyalog, and apply it to the same matrix, we can see that what Joel's created is essentially stencil code, but using rotations, whereas the stencil operator will fill with blanks, which are blanks for character arrays or zeros for numeric arrays. But the stuff in the middle is exactly the same, and that's exactly what you need to do this convolution problem. The last bits are, well, we're going to multiply by the convolution matrix, so these will be numbers, and then the value of each pixel, in this case it would be 9 pixels, the value of each pixel would be the sum of the multiplied values, so that's 9 values summed up. And this is easily done with a plus reduction on the ravel of each of those submatrices. And lastly, to have it as a valid bitmap image, we just cap the values between 0 and 1. So it does that 3 times, once for each channel, and then it will show us the convoluted image. So this is with the edge detection kernel, which is quite neat. Next, I would like to show you the same thing, but let's pretend like we had a large convolution array. I'm going to get rid of this guard and just jump into the stencil part. So instead of using rotate, this one uses square bracket indexing to basically achieve the same effect, but instead of creating a large array, nested array of arrays which can fill up the workspace, this square bracket indexing essentially slices the array up into these stencil sections. And also to be a bit more efficient, he's created these lookup tables of pixel locations inside the pattern. So CX and CY are slightly different offsets used to create our windows, a little 3 by 3 windows. And alpha and omega in this case are x and y values going all the way across the shape of the image. And so for each pixel here, we're going to grab, okay, let's grab a section then. So let's say our x and y values are 70 and 100. We grab alpha plus cx in brackets and omega plus cy. And these are our indices into the lookup table. So now we can index into the lookup tables. And these are our indices into the image. So then we can index into the image, replace this with a semicolon. And this is a 3 by 3 section of the image. It's one of those individual windows. And lastly, Joel just multiplies those windows by the convolution matrix. And once again, summing up the ravel to get the individual pixel values. and constraining between 1 and 0. So it's essentially the same thing, but it doesn't make masses of copies. And you get the same result. So that's quite neat. The last thing I'd like to show you from this example is what I did to have the exact same effect, but using the new or recent stencil operator. So I don't know if this is the exact best way to do this, but it definitely does the right thing. So for each of the channels, we take a 3x3 stencil. We can, I guess, what could we show? Let's show a 3x3 stencil of 3x3 shape of ones. It's easier to see like this, and you get blanks on the edge. But you could also apply functions to this. So 1 plus, and we end up with 2's where the 1's are and 1's where the 0's are. In this case, I'm just multiplying the convolution matrix across each of those stenciled subarrays, then summing up those subarrays to get back to the original size. So if I find you the shape of this, you'll see that we now have a 4-dimensional array where for each pixel in the image we get a 3x3 subarray, which is the convoluted set of arrays. And then we can reduce the dimensionality using plus reductions. If you do it twice, which is what the power 2 means, then we get back to the original size. We cap them off at 1 and 0. The last thing to do is to put zeros all around the edge again, because instead of wrapping around, the stencil function has the blank values or zeros on the edges. We get 1's everywhere, so we get this bright line around the edge if we don't do this. So I'm basically just taking the middle of it and making it black around the edges. But the effect is exactly the same. So that's how you do it nowadays using the stencil operator. Alright, so that's all my advice and examples for when you enter the student competition. I'm just going to quickly show you how to submit your solutions. So once the site is live, and once you've registered, logged in and submitted phase 1 problems solutions which pass the base cases, you'll also be able to submit phase 2 problems from this page linked at the bottom. This content will change by then, and we'll have all the problems listed here, as well as a package to download including a PDF of all the problems and a submission workspace, which I've loaded up the 2018 one here. So contest2018.dws is the name of this workspace. And it contains a submit me function, which on Windows pops you up with a form. I think on other platforms you get like a bunch of lines to input text manually. But all this does is fill in contest, well this year it'll be contest 2019.dialog scripted namespace. So if you're not on Dyalog APL, you can still enter, but you'll have to manually fill in this .dialog file, which is also provided in the phase 2 package. And after that, you can just select that .dialog file, contest2019.dialog, and upload it. You are welcome to submit phase 1 and phase 2 solutions as many times as you like, but I can only guarantee that we'll judge the latest one. We may keep the others. I think other than that, I'd like to reiterate the important dates. The competition will launch sometime in the next few weeks. The submission deadline is Friday the 26th of July. The winners will be announced on Monday the 5th of August, and the grand prize winner and the non-student winner will be invited to attend the Dyalog user meeting between the 8th and the 12th of September 2019. If you would like to see the acceptance talks from any of the previous year's winners, those are available on dialog.tv. I'll also mention the prizes again because they are pretty great. You know, there's large cash prizes for all the top student entries. There's, you know, complimentary registration to the top non-student, and also referral awards. If you don't even, you know, want to go to all this effort, go to a little bit of effort and just tell your friends, you can win equivalent cash prizes to the winners. So that's, you know, imagine if you referred all of the winners. Just how much is that? I don't know, I'm not going to add it up. $6,500 in cash prizes if you somehow miraculously referred all the winners. So again, the important dates I'm just going to leave up here while I wait to see if there are any comments or questions coming in the chat. I think other than that, thanks very much for watching, and keep an eye on dialog.com/student competitions, student-competition.htm, or just Google Dyalog competition and keep an eye out for when the competition goes live. So the next webinar is scheduled for the 16th of May, topic yet to be decided. And oh yeah, don't forget to check when the competition is live sometime in the next few weeks. Thanks very much.